Hello everyone and welcome to the lecture on source transformation. Before we do that, we're going to cover a couple of slides on node voltage and mesh current. And we're going to talk about the techniques for both of those and compare them. And then we'll go into something called source transformation. So the node voltage method includes the following steps. 1, identify the essential nodes. 2, pick a reference node, if you remember that. I usually pick the side where you're going to have the ground as the reference node, and that's usually the negative side of the return voltage source. And in part 3, label remaining essential nodes with voltage values, and you ask yourself these questions, A and B. Any voltage sources between the reference node and any other essential nodes? If so, label with the value of the voltage source. So in other words, that just becomes the voltage. And question B, any voltage sources between two non-reference essential nodes? And if so, combine the source and the two nodes to create a supernode. Step 4, write a KCL equation at any supernodes. Then write a KCL equation at each remaining non-reference essential node where the voltage is unknown. And then we ask ourselves 2 more questions. Are any dependent sources in these nodes? If so, write a constraint equation for each one that defines a variable the source depends upon. And then the second question, do you have any supernodes? If so, write a supernode constraint equation. So constraint equations are basically where you have like a dependent source and it's related to another value, and so that's going to give you a constraint. And basically what that means is you're just going to plug that value into one of your variables in your other equations. So that's considered a constraint. Number 5, put equations in standard form and solve. Number 6, check your solutions by balancing power. Remember, we always balance power. And number 7, calculate quantities of interest. So make sure that you answer the question and calculate what was asked of you. Okay. And the techniques for mesh analysis. So step 1, identify the meshes. And I think we're all very good at that. Number 2, label each with a mesh current. And then ask yourself these questions to do the labeling. Are there any current sources on the perimeter of a mesh? If so, label the mesh current with the value of the source. And again, if it's on the perimeter, meaning that's the only current going through that and it's not actually being shared, that will be the current going through that source. And B, are there any current sources shared between two meshes? If so, create a super mesh by combining the two meshes and erasing the current source temporarily. That's a very, we haven't done this in class, and I'll do an example, but I won't give you one of these for homework. But again, if you have a super mesh and you have a current source that's being shared, it doesn't matter what the two individual mesh loops are, that current source has to be whatever it's labeled. So you just go ahead and assume that that is the current source. Number 3, write a KVL equation around each super mesh and each single mesh where the mesh current is unknown. And then you have to ask yourself these questions. Are there any dependent sources? If so, write a constraint equation defining the controlling quantity for the dependent source. I like this definition a little better than the previous. So again, just to understand what the constraints are, it's because you have this quantity being designated by a dependent source. And then, of course, question B, are there any supermeshes? If so, write a supermesh constraint equation. Okay, number 4, put equations in standard form and solve. And number 5, okay, so everything from step 4 is basically like we talked about your algebra. So hopefully from here you're good with your algebra. Number 5, check your solutions by balancing power using the correct power equation. And number 6, calculate quantities of interest. And then again, we're going to go over 2 slides or 2 or 3 slides just so we can compare node voltage to mesh current analysis on very similar circuits. So here we have a circuit with 3 independent sources. 2 of them are voltage sources and 1 of them is a current source, and then 2 resistors in between. And so here we're doing a node voltage method, and we're asking for the find the power of the 2 amp source. And just so you guys know, we have some interaction here. We're trying to find the power of this source. So we're already given current. We just need to know the voltage drop across this current source. And we use the power generation equation, P equals I times V, to give us that. So that's what we're ultimately looking for. But let's do some accounting here. So we're going to go ahead and look at how many essential nodes do we have. And of course, it says we have 2, and I'll go ahead and designate those essential nodes for you again. There's 1, and there's 2. And it says number of single node KCL equations. Remember, we said that the number of equations, and let's see if I can do this, number of equations is equal to how many nodes we have minus, n minus 1. Put some space on there so it looks better. And so that means that we're going to have 1 equation that we need to solve this. Number of supernode equations. No, we don't have any supernodes. Number of supernode constraint equations. We don't have that either since we don't have any supernodes in here. And then the number of dependent source constraint equations. We don't have any dependent sources. Right? And didn't mean to do that. And then equations needed to find a desired output. Really, we're just, it says we need 0 of 1 equation. Actually, don't know why they're writing it like this. We do need one equation. Right. Equations needed to find a desired output. I don't see how you can do this with a 0 of 1. But you do need at least 1 equation. And that's designated by this. Okay. Now, let's look at the node voltage versus mesh current. And hopefully I can draw okay on this slide. So number of meshes, and this is kind of easy to see. And right now it doesn't really matter which direction we draw this in, but I'm just going to draw it like this. That's 1 mesh loop. This is 2 mesh loops. Number of single mesh KVL equations. And so we don't have any single mesh equations. The number of super mesh. Remember, a super mesh was designated as if you have a current source that's actually shared between two meshes. And so we do have 1. So since we have 1 super mesh, we have 1 super mesh constraint equation. And then the number of dependent source constraint equations, we don't have any dependent sources again. And then so equations needed to find a desired output. We need, and I'm not actually sure what the output means by 1 over 2 here, or 1 to 2, but we do have 2 equations. I think I know what they're saying here in this slide. We have 1 constraint equation, and we have, which is a super mesh equation, and we have 2 equations by the loops. So it doesn't actually say that in the PowerPoint, but it makes sense to me here that we have 1 super mesh to 2 KVL equations. I'm sorry, number of meshes. And that would make sense for the previous slide. Let me go back, where we have 0 constraints, but 1 equation. So that kind of makes sense. He didn't label it, but those 2 numbers actually make sense that way. Okay, now let's go to this slide. So the node voltage method, we're going to look at another circuit and just again do that basic accounting. Using the node voltage method, the number of essential nodes we have here is 4, and see if you can all count them. They're actually labeled for you in those big dots. Number of single node KCL equations, Remember that was n minus 1, so we have 4 essential nodes, so should we have 3 KCL equations that we need. Number of supernode equations is 0. Number of supernode constraints is 0 because we have no supernode equations. And again, the number of dependent source constraint equations. Now in this particular circuit, they did give us a constraint right here. And the constraint is 30Ix. And all we're saying is the voltage of this dependent voltage is dependent on 30 times whatever the value of Ix is, and Ix is actually indicated right over here. So whatever the current is at the 4 ohm resistor here, which is Ix, is going to affect the dependent source. That is what we call the constraint. Right? Because this is not just dependent on this particular loop, whatever current's going through there, it's also dependent upon over here, so it's constrained by that. And so, and again, it'll make sense again, the equations needed to find the desired output. We do not have any supernode constraint equations, and that's fine, so we have 0. And the equations needed to find the desired output is just one equation. Okay, and we're looking at the power for the 4 amp source, and the 4 amp source is right over here. Okay. And so what you need to do is use the power is equal to I times V, and that'll give us the power generated by that source. We're given current, and we just need to find the voltage across that 4 amp source. Now the same thing for the meshes, same circuit. The number of meshes here, we have 3 meshes, and I'll just go ahead and draw them. I know there's a little delay from what I draw to what you see. So we do this. And of course we do this. That's mesh 1, 2, and 3. I'm not actually labeling them as 1, 2, or 3, just marking them for you. Number of single mesh KVL equations. So a single mesh KVL equation would be the same thing as this. No. I'm sorry, there it is, or single mesh with the current on the outside. Any super meshes, we do not have a current source that's being shared by any, so that's 0 and 0. And the number of dependent source constraint equations, it'll be the same dependent source, which is right here. Well, let me just circle it. Now I'll erase all those in a second. And so the equations needed to find the desired output, we need 2 mesh equations. Again, remember, we're just looking for the 4 amp source here. I don't really care what's happening in either one of these bottom loops. I can actually omit one of them, and I would only need 2 equations to get to the 4 amp source. And 1 dependent source constraint. So we do have 1 constraint and 2 single mesh equations, and that would work. Okay. Now this takes us to, and again, that was just a little review, this will take us to source transformation, which is the topic of this lecture and what your next laboratory assignment is going to be. So under what conditions are the 2 circuits below equivalent? We're looking at the circuit to the left and the right. And equivalent means that if you attach any resistor to both circuits, it would have the same current and therefore the same voltage and power. And by where it says attach any resistor to both circuits, we're looking at the load resistor, and that would be, let me try to draw a shape here. We're looking at that, and this, right? So under what conditions? And so the conditions that we're looking at, and let me do this in a different color, is these two conditions, where we have a voltage source in series with a resistor, and we have a current source in parallel with a resistor. Right? So basically what's happening here is those two values of R are equal. What's going to change is the voltage source or the current source, depending on which way you're transforming. If you're going from the voltage source with the series resistor and you're transforming that into a current source with a parallel resistor, then of course your voltage would have to, you'd have to calculate for the current traveling to that voltage and that resistor, and that value would actually equal the current through IS. And we'll get more into that later. But what you're looking at down here in this equation, and let me do this with a straight line. Do I get a line? Yes, I do. So what we're looking at down here is looking at the current through IL equaling VS over R plus RL. And this is really a voltage divider, right? We're looking at R and RL. So R right here and RL right there. Now those two resistors are in series in the circuit to my left, and so that would be a voltage divider circuit. And so the current through IL would be voltage over total resistance. Now if we're looking at the current through RL in the circuit to the right, we're going to do something a little different, where we have to actually combine these two resistors. And let me give me a second while I do another shape. And I will pick purple. So again, we'd have to use these two resistors, if you guys can see this right there. Get the equivalent resistance, and then we can do a current divider equation to give me what the current through RL would be. Again, current divider just means that I am proportioning the current between that network, and on a certain proportion of it will go to RL, and a certain proportion will go through R. And so basically we're looking at a voltage divider or a current divider circuit here. But the whole point of transformation here is to prove, and we can plug in values into these later, that it would be the exact same thing. Whatever that voltage and resistor in series would be equivalent to that same current source and that resistor in parallel. And that's going to actually make it easier for us to do circuit analysis, and we'll see that in the next slide. Well, in a couple of slides. So just a quick review. The condition for source transformation is using Ohm's law, which is V equals I times R, or R times I. Again, just simply Ohm's law. And this says this is false. I think I didn't read that properly as a question. Right. Even though you do use Ohm's law to calculate for current here, and Ohm's law is one of your basic tools, this is a little more than Ohm's law. Okay, and so let me show you what this would look like if you're actually going to use source transformation to simplify or analyze a circuit. So we have a circuit up on top. It says source transformation. Find V in the circuit below by using a sequence of source transformations. So we're going to do this with using very little calculation, using very little pen and paper or calculator. A lot of this stuff you can do in your head, and I'll show you how we do it. So remember, we're going to look for the voltage across this 8 ohm resistor. And again, your technique may be a little different. You may start off in one part of the circuit versus another, and you'll see what I mean when we do this. But that's okay, as long as you get to the end result and your analysis was, you used the analysis appropriately. So step 1, source transform the 2 leftmost branches in the circuit from series voltage sources to resistor, and source transform the 2 leftmost branches in the circuit from series voltage source and resistor to parallel current source and resistor. So remember the circuits we saw before, we had the voltage source and a resistor in series. We're going to change that to parallel with a current source and a resistor in parallel. So let's go ahead and look at these two right here. Now you can see we have one, where's my pin? We have this voltage source, and it's in series with a 20 ohm resistor. And then we have a 5 ohm resistor that's in series with the 60 volt source. And so what we can do is, by looking at that individual branch, and there's nothing else in that branch, we can actually convert that to a current source with a resistor in parallel. And so the way we do that is just isolate that branch, that 120 volts and 20 ohms, and say how much current would be flowing through that 20 ohm resistance. Using Ohm's law, remember we're using Ohm's law, we can find, and let me type this up here. Hey. All right, so we know that V is equal to I times R, and there seems to be a delay in what I'm typing. Yep, big delay. But hopefully, I don't know how that's going to look like in the recording. So we can actually just isolate for R, use your algebra, and then set I equal to V over R. That gives us 120 volts divided by 20 amps. And that equals to 6 amps running through that branch. So what I can do right now is go ahead and change that voltage source into a 6 amp current source. Now, again, this is just for analysis. We're not physically changing this in the circuit, but we're just doing this for analysis. So we're going to go ahead and on paper put a 6 amp source, and that 20 ohm resistor is going to go in parallel. And let me just draw that here. So here's my 20 ohm resistor that was up here on top, right? And so now we took that first branch of the 120 volts and 20 ohm resistance, and we converted it to this network right here. And I'm going to, well, that's good enough. Now we're going to do the same thing. I'm going to just do this in a different color. We're going to go ahead and take the 60 volt and 5 ohm resistor, and then we're going to convert that into a current and current and resistor in parallel. And again, this, I meant to draw a square. I know you guys can't see this, but there it is. You should be able to see it now. We have a 60 volt divided by 5 ohms to give us 12 amps. So I'm going to go ahead and write a 12 amp source here in parallel with the 5 ohm resistance. Now this is actually equivalent to that series element of a 60 volt source with a 5 ohm element in series. And so now what do we have? We leave that 36, let me see, this 36 amp current source is already in parallel with the 6 ohm resistor. So guess what? Now we have 3 sources, current sources in parallel with 3 resistors in parallel. And let's keep going to the next slide. We're in slide 10. So step 2, combine the 3 parallel connected current sources into one current source. And why do we do that? Because we know that KCL says that current going in through any parallel network has to equal the total current. So we can just combine all those currents that are in parallel together. And I didn't look at the individual values, but there it is, 6. We had minus 12 and 36. And so we have 30 amps going in this direction. Now we're still left with that resistor network on the at the far right. Now we're looking for the voltage across that 8 ohm resistor. And how do we do this? Now from this, you can actually do this from some of your older methods that we learned in chapter 2. But let's go ahead and do another source transformation and go backwards so that we can simplify this circuit. So what I'm going to do is I'm going to go ahead and show you. We're going to take this resistance, this 2.4, I'll leave it like right about there. That current source and that resistor in parallel, let's go ahead and change that to a voltage source and a resistor in series. So the same thing. If I have, 30 amps and 30 amps is going across this resistive network, what do we have? Which is 20, 5, and 6. I can't remember the actual values here. 25 and 6. Give me 1 second, guys. I don't know why it's just throwing me off. Okay. So anyway, let's go to step 3. And so again, we're going to change this current source and this resistor in parallel to a voltage source and resistor in series. And so we know we have 30 amps and 30 amps going into 2.4 volts. Now for this last step, remember we don't, there you go. So right now for this 8 ohm resistor, we just go ahead and pretend it's not there when we're doing these transformations. So go ahead and ignore that the 8 ohm resistor is here. This load can be anything. It can be an 8 ohm resistor, a 10 ohm resistor, a 50 ohm. It doesn't really matter. The reason we're taking it off is because we want to create a network that where we can plug in any kind of load, and we should be able to predict what's going to happen to that load. And so we take off this load just for the calculation, and since we do that, this 1.6 ohm resistant here, where's my line? Right? If we had this 1.6 ohm resistor right there, I'm trying to draw an arrow, we would actually have no current flow going there. I don't know why I drew that arrow. I was trying to say, is there current flow going through here? No, we wouldn't if we didn't have this 8 ohm resistor here. And so since we're, for the analysis portion, since we're doing this as if we have no load, as if we don't have this 8 ohm resistor, we're not going to get any current through this last branch. So every time you have a resistor in the very last branch going to the load, you're going to go ahead and ignore that for the analysis part, just to get the last transformation. And so we have 30 amps times the 2.4 ohms in parallel. We're assuming all the current's going through that 2.4 ohms, which is the max that could go to the 2.4 ohms. And we get a 72 volt voltage drop. And so then we go ahead and do the source transformation and create a voltage source, which we have down here. Let me do this again, right there. I'm right here. So now we can write a 72 volt independent voltage source in series with a 2.4 ohm. Once we get to this point, we can actually go ahead and put the rest of the circuit back together, which is the 1.6 ohm, which will be in series with, in this case, is the 8 ohm load, right? And so step 4 says use voltage division to find V across 8. So voltage across the 8 ohm resistor, we use voltage division right down here, and we end up with 48 volts, and that should be some simple algebra. All right. So again, it is possible to perform source transformations to simplify any circuit. And again, anytime you see something that says always or any or gives you any absolutes, the right answer is usually false. Okay, and understand that I said is usually false. Even there, it's not always false. So let's go ahead and go to the last 2 slides. And let's see, we're going to do a source transformation. This is just a different circuit. Find V0 and the source power in the circuit below by using a sequence of source transformations. And so we have the voltage source and 125 ohm resistor here that are in parallel. I'm just going to mark it there. But we can't do anything with that, right? We need a voltage source with a series resistor, okay? Now over here we have a current source with a resistor in series, and we can't do a transform with that because we needed a current source with a resistor in parallel. Right? That didn't work either. But we're going to do something a little unique here. So it says remove the resistor in parallel with a 250 volt source. Now this is a little trick, and I won't give you something like this for homework, but it's good for us to cover it here. So what they're doing here And let me put this in a different color so you can see this, so it'll stand out. This 125 ohm resistor. All right, let me erase all this stuff. There you go. This 100. Come on, there it is. They took out this 125 ohm resistor. Anybody know why? That's great. I'm sure some of you are thinking it already. I have 250 volts in parallel with the 125 ohm resistor. So what that tells me is I have 125 volts at that node up there on top. So it doesn't really matter that that resistor is in parallel with the voltage source, because I have I'm still having 120 voltage, a 250 volt voltage drop, excuse me, across the 125 ohm resistor. So because of that, we can actually pretend the resistor is not there, just for analysis. Of course, the resistor is actually there in real life, but for the analysis, we can say technically we do have 250 volts at the node where the 125 ohm and 25 ohm resistor actually connect, which is this little guy right there. Okay, so that's why the 125 ohm resistor is removed here. You can do that when you have a 250, when you have a voltage source and a resistor in parallel. So it says remove the resistor in parallel with a 250 volt source, since it does not change the voltage drop between the top and bottom nodes on the left. Then it says remove the resistor in series with the 8 amp current source, since it does not change the current in that branch. Again, remember, we're only doing this for analysis so we can find out what the current and the voltage sources are, the impact is. So in this branch, and I'll do it in a different color, right here, we have 8 amps going through this 10 ohm resistor. So what does that mean? The current through this branch is always going to be 8 amps. So we can remove that resistor since it doesn't really affect the 8 amps. Again, this is just for analysis, not on paper. So now we're looking at something that looks like, I'll do this in a different color, like this. A voltage source and a current source that do not have their neighboring resistors. So that's a nice little trick to actually simplify the circuit for analysis only. Okay, so what do we have now? We have a voltage source and a current source. Let me erase this because I'm going to be drawing all over the place. No, I'll do it in a different color. We have a voltage source and a resistor that are in series, and we have a current source and a resistor that are in parallel. But we may not have to do anything with that that second network to simplify. Let's see what happens. It's kind of exciting. Okay, did I actually go to my next slide? 13 and 14. Okay, so source transform the series connected voltage source and resistor on the left, and combine the two series connected resistors on the right into one equivalent resistance. Okay. So we added the 5 and the 15 resistor that was over here to give me a 20 ohm resistance. We source transformed that voltage and the 25 ohm resistor to give me a current source and resistor in parallel. And look at all this. Now we have two current sources going in opposite directions in parallel. We know what we can do with current sources in parallel. We can add them. And then we have these other resistors that are all in parallel. And so we can actually combine them if we wanted to. So step 3 says combine two parallel current sources into one source. And since we had 25 in one direction, I'm sorry, I don't want to say 25, 10 amps in one direction and 8 amps in the other direction, we get 2 amps. And so we have a 2 amp source going up. Now it says the 3 parallel resistors, combine them into one resistance. So we have a 25, 100, and the 20, and that gives us a 10 ohm resistance right here. And so now we have a current source and we have a resistor. Now remember the voltage drop across that top node, not just one more color so you can see. This whole thing is the same electrical reference, so it doesn't matter what point we're measuring, we're still going to be measuring that V sub naught. So if we take that reference from there to here, from the top to the bottom, this V sub naught, and let me do this in a circle. This little V, oops, I don't think I can move it either. No. Circle doesn't work the same way. That V sub naught right there will be the same because everything's in parallel. So now we just use Ohm's law. V naught is equal to 2 amps times the equivalent resistance of 10 ohms to give us 20 volts. So V naught equal 20 volts. And then again, the last step was to check power and balance power to make sure everything is working. So what you could do is find all the power being generated by the sources, the initial sources, and look at all the power drops across all the loads, all the resistors, including the load, and they should all balance out. You should have, in this case, a resultant of 0 watts. Right. And I'm not going to do this part. You guys know what a power generation equation looks like, I times V, or V times I, and then the power loss or power drop equations, which is I squared times R, or V over R. Okay. And that concludes this part of the lecture for source transformation. I hope that you enjoyed this, because this is actually very, very cool. Makes things look really easy. It helps you take a complex circuit and simplify it into a simple circuit. Now you can use a lot of your parallel and series theorems to actually simplify the circuit and work it the same way you did before that you learned in chapter 2 or in the first couple of weeks. However, it would probably mean a lot more accounting and keeping track of a bunch of little things. This way you can kind of do a lot of this in your head if you can see how these transformations work. And that's it. Hope you enjoyed it, and we'll see you with Thevenin circuits.